We now begin to look at what happens to the root locus when it is not on the real axis, and we develop our second general plotting rule. And with the first and second rules alone, we'll be able to plot many root locus plots pretty accurately. And then we'll see that there are some refinements that we can do with some of the other rules. But first we make an observation. Our system models are rational polynomial. In other words, they have a b of s divided by a of s. And these polynomials have real coefficients. And this restricts the poles to either be real or to come as complex conjugate pairs. And so one thing that means is if I plot my S-plane, if I have a pole up here somewhere, I must have a corresponding pole down there somewhere. There has to be a symmetry above and below the real axis. So this does help, but it's not truly sufficient for filling in what happens with complex conjugate poles as k goes from 0 to infinity. So we've looked at what happens on the real axis. Now we're going to consider what happens in the limiting cases when k is actually equal to 0 and k is equal to infinity, or maybe more precisely, the limit as k approaches 0 and the limit as k approaches infinity. And to think about that, we write 1 plus kg of s equals 0 in two different ways. First, I'm going to write it as denominator, so this is equal to 1 plus k times b of s over a of s equals 0, and I'm going to first think about it by multiplying both sides by a of s and getting this method, which is a of s plus k times b of s equals 0. That's the first way to think about it. And when I do that, I've got all of the poles, and plus k times all of the zeros equals 0. And if we take the limit as k approaches 0, what happens is that all of this goes away. And I simply end up with the product of the pole locations equal to 0, or the closed loop pole locations when k approaches 0 equal the open loop pole locations of the original transfer function. We've actually noticed that in all the root locus plots we've drawn so far is because we start by plotting the open loop poles and zeros, and we noticed that when k was small, the root locus was actually right at the open loop poles and zeros, but it only moved away from there as k got bigger. That's what happens when k approaches 0. That's the somewhat easier case. When k gets really big, though, when k approaches infinity, we need to rewrite the expression a little bit differently. So I take this equation here, and now I divide both sides by k, because if k goes to infinity, 1 over k goes to 0, and that's easier to think about. So I would end up with then a of s over k plus b of s equals 0 is an equivalent form, and as k goes to infinity, all of that stuff goes to 0. And over here, all of these get wiped out. So what I end up with is that the closed loop pole locations eventually, as k gets turned up, converge on these roots, which are the open loop 0 locations. Now, if that's all there were to it, that would be easy, but usually in most transfer functions we have that the number of zeros is usually less than n, not always, but usually less than the number of poles. And what is a little bit sneaky is the fact that there are in fact the same number of poles and zeros, but some of the zeros are hiding. So let's take an example here. Let's suppose I have a transfer function s plus 5, I'm just making this up, over s plus 3, s plus 2. Okay, so if I asked you what the poles and zeros were, you would probably say, oh, well, there's a pole at P1 equals minus 3, P2 equals minus 2, and Z equals minus 5, and would be done. But in fact, if I say that what happens when s equals infinity, when s itself goes to infinity, would have to say, ooh, well, what would happen? Well, let's write it this way. Let's divide numerator and denominator by s squared. That would probably be a good thing to do. So if I divide numerator and denominator by s squared, I've got 1 over s squared times s plus 5, and 1 over s squared I'm going to factor in, which is going to be 1 plus 3 over s, and 1 plus 2 over s. And in the numerator, I could say, well, numerator is going to be 1 over s plus 5 over s squared divided by 1 plus 3 over s, and 1 plus 2 over s. As s goes to infinity, that denominator term goes to 1, which is a perfectly valid number. That denominator term goes to 1, which is perfectly valid. And the numerator, you'll notice, goes to 0. So it looked like there was 1 0 and 2 poles, and in fact there was 1 finite 0 and 2 finite poles, but there's also a hidden 0 at infinity in this transfer function. And in general, there's going to be n minus m of these hidden zeros, and they're all at infinity. Okay, well, infinity in terms of the real number line is something that's fairly easy to think about. It's just way off to the right, but way off to the right, or maybe it's way off to the left. Is it plus or minus? Well, that matters. In the complex plane, infinity is in any direction. It's a little bit more tricky. So I kind of think of the complex plane as a beach ball, and maybe that's not a great example, but the origin here is the part of the beach ball where you have that nozzle that you blow into to inflate it. But it doesn't matter which direction I go to. I can go in that direction for an infinite distance, or that direction, or that direction, or that direction. Whichever direction I go in the complex plane, if I go far enough, I am going to get to what we call complex infinity. And it's the other side of the beach ball, if you will. It's just a very, very big beach ball. There's probably some mathematicians who would say that's a terrible way of thinking about it, and they're probably right, but that's the way that I think about it. In any case, we have, in our example of the root-locus plot, when k equals 0, the poles start out at the open loop poles. The closed loop poles start out at the open loop poles. And as I turn k up, as it gets bigger and bigger and bigger, eventually these closed loop poles are going to converge on the open loop zeros, including those open loop zeros at complex infinity. And so the ones that are at finite places are a little bit easier, but the ones going to complex infinity we have to think about a little bit harder. Which direction in particular do they go? Do they go up? Do they go down? Do they go left? Do they go right? And so forth. So what we have to do is we have to look at kind of an asymptotic or a limiting case. Suppose you're standing at infinity. You're standing very, very far away from the origin in the S-plane. And as you look toward the S-plane, if I'm standing close to the S-plane, it might look like I've got some poles and some zeros, something like that. That are all, I can very, very distinctly tell them apart, but as I get far away, these are going to all kind of scrunch together. As I get farther away, they're really going to get scrunched together into some blob, and if I'm standing at infinity, it's really going to look like, instead of, in this case, 3 poles and 2 zeros, it's going to look like basically 1 pole that I can see, because 2 of the poles and 2 of the zeros, if I'm standing far enough away, have pretty much canceled each other out. Those finite poles have ended up on the finite zeros. So if I stand very, very far away, what I have is approximately the remaining uncanceled pole at location alpha, and they all look like they're at the same location, wherever that is. And my transfer function looks like 1 plus k times 1 over s minus alpha to the n minus m. In other words, I have m poles went to the m zeros and basically got canceled out. N minus m poles all look like they are at s equals alpha, roughly speaking, looking back from infinity. So that's approximately what we have. That's our approximate transfer function. And so what we're going to want is we're going to want to know where is that alpha? Look, standing back at infinity, where does it look like these poles are starting from? That's the center of the locus of these poles that go off to infinity. Then I also need to know not only the center, but then the directions that these poles take as they approach infinity. So what we're going to do is I'm going to assume that some point is on the locus, and this is my test point S1, and I'm going to write S1 as a magnitude and a phase. So R is the radial magnitude away from the origin, and phi is the phase or the angle of this pole. And I'm going to use geometry to see what phi must be for S1 to be on the locus. And so again, we're standing pretty far back, and I'm looking here of very big radius. So these are not the finite poles and zeros, which are all kind of back in here and canceled out. I'm looking at, can I sweep this angle for this very big R? Can I sweep this angle phi until I intersect somewhere that I find this value S1 that's on the locus using the angle criteria. So where is G of S equal to 180 degrees for some value of R and phi? Okay, well, since all of our open loop poles are approximately at the same place alpha, then we have that the angle of 1 plus k of G evaluated at this test point is 180 degrees if the n minus m angles starting at alpha and ending at S1 sum to 180 degrees. So I have n minus m angles starting at the same place, and they all need to equal 180 degrees plus maybe 360 or plus 2 times 360 or whatever, because angles are repetitive in that sense. Then I solve for phi L. Phi L is 180 degrees plus 360 times L minus 1 over n minus m. In this case, L goes from 0 up to n minus m minus 1. I could also have, in this case, L starting at 1 going up to n minus m. This is our equation for the angles. I have poles that are starting at alpha and are proceeding from alpha with these particular angles toward infinity, and that's what it looks like when I look back from infinity. Let's put in some numbers. If n minus m is 1, that means I've got one more pole than 0. I plug that in. I got L goes from 1 to n minus m, 1 to 1. There's only one of them. And then I have n minus m in the denominator is 1, so phi is 180 degrees plus 0 divided by 1, or 180 degrees. Done. There's one pole going from alpha to complex infinity along the negative real axis along 180 degrees, and I don't know if you can see it, but that's what that plot is trying to show. I've got a pole going that way, starting at some value over here, maybe alpha. If I have two more poles than 0, then we're going to put in n minus m as 2. I'm going to have L going from 1 to 2, and I'm going to have 180 degrees plus 360 times 0 all over 2. And then I'm also going to have 180 degrees plus 360 times 1 over 2. The first one is 180 over 2, which is 90. The second one is 180 plus 360 all over 2, which if you do all the math ends up being the same thing as minus 90. It's 270 degrees, which is the same as minus 90. And that means I've got two asymptotes, two poles going off to infinity, starting at alpha, and one goes straight up at 90 degrees, one goes straight down at minus 90 degrees. And we've seen root-locus plots like that before a number of times, where the poles just kind of take off and go up and down. If I have 3 more poles than I have zeros, you plug into that equation, you get asymptotes at plus and minus 60 degrees. That's 60, that's minus 60. And then there's another one here that might be hard to see that's at 180 degrees. And so forth. You can figure out similar patterns for 4 and 5 and 6 and however many more you might have. Now that tells you which directions the poles go toward infinity. Now we figure out what is the center, alpha, the centroid of the poles going toward infinity. Now notice that the roots of the denominator polynomial of g of s of the open loop system satisfy this equation here. So I've got I can just write it out as a polynomial s to the n plus a1 s to the n minus 1, etc. That's our standard polynomial written out form, and this is our factored form. And if I take the thing on the right and multiply it out, I'm going to have s to the n, and then I'm going to have the sum. I'm going to have minus p1 s to the n minus 1 minus p2 to the s n minus 1, etc. So I'm going to have minus the sum of pi all times s to the n minus 1, and then plus things taken pairs, and then minus things taken as triplets, and so forth all the way down. But what we're interested in here was just noticing that the coefficient of the s to the n minus 1 term is minus the sum of the poles. So keep that little factoid in your mind. We're going to use that. And that's the open loop transfer function. That a1 value can be determined from that. And then if you look at the closed loop transfer function, we say, okay, the roots of the denominator of closed loop are a of s plus k times b of s equals 0. And if n minus m is bigger than 1, by the way, if n minus m equals 1, back in this case, we already knew how to do that. That was the real axis rule that said everything to the left of an odd number of things went off to minus infinity on the real axis. So we knew how to do that one. Now we're looking at, well, what about these cases? Where is this alpha that determines this? So if n minus m is bigger than 1, that means that this s to the n has no correspondent in this k times s to the m and so forth over here on the right. And this s to the n minus 1 also has no correspondence in the poles over here on the right. It's not overwritten by any of these terms. And so that means that in the closed loop system, the a1 term is also equal to minus the sum of the closed loop poles, just by the same analysis. So A1 is the sum of the open loop poles. It's also the sum of the closed loop poles. Okay, well, of the closed loop poles, we know that m of them go to the zeros of g of s and get canceled out. But the other n minus m are clustered, we've said, at the centroid location, 1 over s to the s minus alpha to the n minus m. So the sum of the roots, I've got n minus m of them at alpha, and I've got the rest of them at the open loop zeros. Okay, the open loop zeros provide these, and the rest of them provide those. So that's the sum of the closed loop pole locations. So I put all of this together. So the sum of the closed loop poles equals, well, all of these guys. Again, this was without the minus sign in front of it, so that's why the minus went away. I had a minus here, and a minus there, and minus there, and minus there. So multiplying everything by minus 1, I have sum of the closed loop roots we have said we're approximating as n minus m times alpha plus the sum of the open loop zeros equals, because a1 equals a1, the sum of the open loop pole locations. And so I can solve for alpha. Alpha is equal to the sum of the closed loop pole locations minus the sum of the open loop pole locations minus the sum of the open loop zero locations, all divided by n minus m. So those are the two critical things we need. If I'm drawing where the root locus goes as k gets really, really large or k gets really, really small, we have our general rule number 2, that all poles go from their open loop locations at k equals 0 to either the zeros of G of S, or, when those are exhausted, to complex infinity. And those going to complex infinity go along asymptotes that are centered at alpha, which is the sum of the pole locations minus sum of open loop zero locations over n minus m, and they go along certain angles. So that brings us to a couple of examples. And we now have enough information to look at this and to at least have an idea of what these root locus plots look like. Maybe not in precise, infinite detail, but we can get a pretty good idea. So let's look at the example that's labeled 1. So first think about the real axis rule. Where is the root locus on the real axis? So I'm going to say, okay, consider a test point on the real axis that's moving to the left. As I move it to the left, I've started here, and we see, okay, I'm not to the left of an odd number of anything, so it's not there. I move along. I haven't encountered any open loop poles or zeros yet. Oh, all of a sudden I come across some open loop poles, but there's 2 of them at once, so I go from, as I count, going from right to left, I count from 0 to 2 things, which is still even, and so nowhere on the real axis do I have a place where the root locus exists. Okay. Now, the next rule, rule number 2, says that the closed loop poles start at the open loop poles. Well, the open loop poles are drawn, so we're always going to draw our open loop poles first. And as you can see, I've got them plotted right there and right there. But then they say they are going to go to plus minus infinity along certain asymptotes. And so first, how many asymptotes are there? Well, it's the number of open loop poles minus the number of open loop zeros, which is 2 minus 0, or 2. I'm going to have 2 asymptotes. And what are the angles of the asymptotes? Well, if there's 2 of them, the angles are plus and minus 90 degrees, we said. So I'm going to have poles going straight up and straight down. But where are they centered? So then I have to find out alpha. So alpha equals the sum of the pole locations minus the sum of the zero locations, all divided by n minus m, which is 2. So the pole locations are over here. I'm going to call that value here beta, and I'm going to call that value here gamma. And so I have a pole location at beta plus j gamma plus beta minus j gamma, and then there's no zeros, so plus 0, all over 2. And one thing you notice is that the complex part cancels, so the j gamma and the minus j gamma go away, and I get 2 beta over 2 equals beta. So guess what? Our alpha location, our centroid, is actually equal to, in this case, the value on the real axis right there that is dead between these. So that's the center point, and then I take my ruler and I put one part of the ruler on that center point, and I draw 90 degrees out toward infinity and 90 degrees, minus 90 degrees out toward infinity, and that's what that root locus looks like. One of those poles just goes straight up, and one of them goes straight down, and that's all there is to it. That's example 1. Now example 2. In example 2, we again start with the real axis rule. And we start with a test point on the real axis, and we move it that way. And I guess the first thing I did, is I plotted the open loop poles and zeros, and we have them there. And so as I'm moving that test point, I'm not to the left of anything, and I can go beyond the poles. I'm still to the not to the left of an odd number of things. That's an even number. It's only after I pass the 0 that I'm to the left of an odd number of things. So this part here of the root locus, the real axis, is on the root locus, and that just goes off to minus infinity. Now, at the moment, that looks weird because it looks like my zero is moving, and in fact, we know that feedback does not move zeros. So something else is happening, and we'll see what in just a second. The next thing we consider is how many asymptotes are there, and there's n minus m asymptotes, which is 2 minus 1 equals 1. So what we have is we have a situation where there are 2 poles, 1, 0, and there's going to be one asymptote going to infinity. We know that one of those poles has to end up at that open loop 0, and the other pole has to end up at infinity, which might seem strange. You might have to scratch your head a bit and think about, well, how could that happen? We also know that everything above the real axis must be mirrored by everything below the real axis. And so for that to happen, the details may not be exactly this, but in generality, we're going to have some pole looping around, coming down. The other one is doing the mirror, and then one of them is going to go to the 0, and the other one is going to go off toward infinity along the direction of the negative real axis. That one's kind of sneaky. You might not have expected that one, but that's what that root locus does. Now example 3. Example 3, I've plotted the open loop poles and zeros of the system. There are 3 poles, no zeros. And so I have, by the real axis rule, I do my test point, I move it toward the left, and by now you should be getting pretty fast with this. So you could say, oh, the real axis is part of the root locus on this segment here, and that's just going to go off that way. And then you figure out how many asymptotes are there. Well, n minus m, n minus m equals 3 minus 0 equals 3. So there's 3 asymptotes. I go back to the picture, and I remember that one of the asymptotes is at plus 60 degrees, one is at minus 60, and one is at 180. Well, we've already seen the one at minus 180. That's 180 degrees. That's this one right there. So I need to figure out where the other asymptotes are centered. So I didn't give you a scale on this, so let's just suppose that the real part of that is beta and the real part of this is 2 beta, just to have an example. So we're going to say, obviously in a real problem you would have real numbers and you put those in, so this is just a sketch here. So alpha equals the sum of the poles minus the sum of the zeros divided by 3. Because there's 3 more poles than there are zeros. So sum of the poles is going to be beta plus its imaginary part plus beta plus its imaginary part. Those two cancel from those complex conjugates, so I don't even put the imaginary part in. And then plus 2 beta from the other one, all divided by 3, and that's equal to 4/3 beta. So my alpha is somewhere around there. And then I draw my angles like that, plus 60 degrees, minus 60 degrees. That is not the locus. That is the asymptote. The locus approaches that. The actual locus is going to start at this pole, and it's going to approach that maybe a little bit more carefully than I've drawn there. Let me try that again. I'll draw my minus 60 degrees, and then the asymptote is going to approach that and converge on that, and this one is also going to approach and converge on it as k gets bigger. So that's how that system is going to work. You can see that systems having more poles than zeros, if they have 3 more poles than zeros, I'm guaranteed that some of those poles are going to eventually go into the unstable right half plane. And so designing controllers for systems with lots of poles becomes tricky because you have to somehow entice those poles back into the left half plane for things to be stable. So that's what that root locus plot looks like. Example number 4. So over here, again, the open loop poles and zeros are drawn for you. We look at the real axis rule and realize that the locus is on the real axis between those points right there. I look at how many poles and zeros there are and say there's 3 poles and 1 zero, so there's going to be n minus m equals 2 asymptotes. I'm going to have asymptotes that go straight up and straight down. And then I have to figure out where is the centroid of those. And again, just for example, let's call that beta, call that 2 beta, and call that 3 beta, just to have numbers. So I have alpha equals the sum of the poles, which is beta plus beta for those two complex conjugate poles, plus 2 beta for the real pole, and then minus the zeros. So that's minus 3 beta for that 0 location, all divided by n minus m, which is 2. So I've got 4 beta minus 3 beta is beta, so that's equal to beta over 2 is my centroid location, at least roughly speaking. So that's going to be where my alpha is. And so my asymptotes are plus minus 90 degrees going through alpha, and then the real locus is going to do something like that. So those two poles are going to eventually go straight up and straight down, but first they are going to take a little excursion, and then the other pole goes toward the other 0 along the real axis. And then for now, we have one more example. And in this example, there's 2 zeros and 2 poles. And notice that the system is open loop unstable because the poles start out in the right half S-plane. And it would be nice if somewhere on the root locus we could find places where both poles were in the left half S-plane, meaning the closed loop system was stable. And it would be even nicer if we could get them in places that satisfied our performance specifications. So first order of business is finding out where is the axis, the real axis on the locus. So I start out with a test point and I move it. Where I've drawn it, it's to the right of everything, so it's not on the locus. And then I move it toward the left, and I'm to the left of the odd number of stuff here, up to there, and then from there up to there. So those are places on the real axis where the locus exists. We might be tempted to think we're done. It's like, okay, I've got something going to something. But looking carefully, we say, oh no, I can't have a pole terminating on a pole. I have to have poles terminating on zeros. So something else must be going on that I'm not aware of. So in fact, this pole is moving that way, and this pole is moving that way. And then something must happen. They must leave the real axis because they can't keep going that way. In fact, somehow they have to get over to the other side to where the zeros are. And so at some point, these poles are going to split and leave the real axis. And in fact, it's going to look something like that. That the poles come together, they split, they cross over into the left half S-plane, they come together again, and then they split, and one goes to that 0 and the other one goes to that 0. So, using only 2 root locus rules and a little bit of thought, you can come up with approximate root locus for all of these systems. And some of these were kind of tricky. Number 2 and number 5 here were especially tricky. So we're going to come up with a few more rules that help us in the tricky cases to be a little bit more exact, understanding how the locus works. But even with these 2 rules, which are not hard to implement, frankly, the real axis rule, I just have to count odds and evens. And this rule here, I have to count how many more poles than zeros are there, so I know what directions things go, and then I have to do that simple formula of alpha equals sum of poles minus sum of zeros over n minus m. Really, really simple formula to find the center. We can get a pretty decent root locus just from that. So our next step is to clean up our technique a little bit, to add some slightly more advanced refinements to help us with our root locus plotting.